Morning. This is Muhammad Hawa. Today we discuss the concept of Fourier series. This is a very important concept in signal analysis. We'll only look at the concept in this part and then we'll discuss the equations in the next one. Let me first remind you that in certain cases we'd like to represent a certain signal using the sum of other signals. A popular example is the Taylor series expansion of a signal x of t at a certain point, which you are probably familiar with. Notice that I could represent the signal x of t as a summation of multiple signals. One result of this Taylor series expansion that you've seen we talked about in complex numbers is the exponential function, and you can write the exponential function using this power series. Similar to this, in Fourier series, we represent a certain periodic signal x of t as the sum of many sinusoids, like cosines and sines, which we call, by the way, harmonics, plus an extra DC component, which you'll see later on is called the average value. So in a nutshell, the concept of Fourier series is that if you have x of t periodic, you can write it as an infinite sum, as you can see here, of sinusoidal signals. In addition to the sinusoidal signals, typically you need an extra DC value, which we have here. The frequency of each of those sinusoids, the nth sinusoid, which we call the nth harmonic, is actually an integer multiple of the fundamental frequency. So the frequency of the nth harmonic is n multiplied by omega naught, where omega naught, as we discussed earlier, is the fundamental frequency. How do we calculate the fundamental frequency? It's 2 pi over the fundamental period for the signal x of t. So what Fourier series is telling us is that x of t periodic is actually not one frequency. It's actually multiple frequencies, because you can write this x of t periodic as an infinite sum of sinusoidal signals, and each sinusoidal signal has a certain frequency, omega n. But those frequencies are related to the fundamental frequency of the x of t that is periodic. What else do we need to know about sinusoidal signals? We also need to know the amplitude and the phase. The amplitude and the phase of the nth sinusoid or the nth harmonic are dependent on what periodic signal x of t that you are dealing with. So if you are dealing with x of t repeated rect, you'll get certain amplitudes for the cosines and the sines, different than if you're dealing with repeated triangular or repeated sawtooth. Every time you change x of t periodic, you are getting different amplitudes and different phases for those sinusoidal signals. Before I show you a visual illustration of this important concept, please remember that I can write this idea, this concept, using 3 mathematical equations. All of them are valid. They express the same idea, that if you have x of t periodic, then you can write it as infinite sum of sinusoids. But the reason we have 3 different equations is that each one of those equations has certain advantages and disadvantages. That's why you have to remember all of them. Those equations are called the complex exponential Fourier series form, the complex exponential Fourier series form. You can see x of t is infinite sum. We have the sum here. N equal minus infinity to infinity. Alpha n e to j n omega naught t. This j here is the square root of minus 1. So you see why we call it complex. And this is the exponential function. So we call it the complex exponential Fourier series. The alpha n's that you're getting, called Fourier series coefficients, are actually complex numbers. They have a magnitude and they have a phase. But please notice that each harmonic here has a frequency n omega naught. It's multiple of the fundamental, where the fundamental frequency of the periodic signal is 2 pi over t naught, the fundamental period. Another way we can write the same concept is the trigonometric Fourier series form, where we write x of t as infinite sum, but this time we use cosine n omega naught t and sine n omega naught t. This cosine n omega naught t is multiplied by a constant an, and this sine multiplied by a constant bn. We call an and bn the Fourier series coefficients for the trigonometric form. This is the extra DC value. So notice what we're saying. We're saying that x of t periodic is an infinite sum of sinusoidal signals plus an extra DC component. The final form is called the compact Fourier series form. And notice here I replace the cosine and sine with just a single cosine, which has frequency n omega naught t. But this cosine has an amplitude Cn and a phase shift minus theta n. There is also this DC component like I have here. Hopefully I'll show you what is the difference between those equations. You'll see they are quite similar. What they are saying, all of them, is that x of t, if it's periodic, you can write it as infinite sum of sinusoids, where those sinusoids have frequencies multiple of the fundamental frequency. And notice I add up from n equal 1 to infinity, and then there is this extra DC component, this extra average value, which I add to that infinite sum. As I said, each one of those forms has its advantages and disadvantages. That's why it's a good idea to understand all of them. For example, in the complex exponential form, a lot of times we just have to do one integral to find this coefficient alpha n. I know we use complex numbers, but it's just one integral. Here, you have to do two integrals, one for an, one for bn. One for an, one for bn. So sometimes you save a little bit of time when you calculate that integral. Plus, with the integral, you use the exponential. Sometimes it's easier to work with that integral compared to using the cosine and sine. However, the disadvantage is that you're using complex numbers, which sometimes requires a bit more practice. Here, you're using real valued numbers, so newcomers think this is easier to work with when they find the an and the bn. However, because this is using complex numbers, it looks more similar to Fourier transform, which we're going to talk about later on. That's why if you use complex numbers in Fourier series, you get answers similar to Fourier transform, and that makes memorizing things easier. It makes also the properties of Fourier transform easier to map into properties for Fourier series. This one here is sometimes seen as more intuitive because it has a cosine with amplitude and a phase shift, and it's just one cosine, not cosine plus sine. Drawing addition of cosine and sine is not always straightforward, while drawing a cosine with a phase shift is much easier for students. However, finding Cn and theta n, we don't have a direct integral to find them. You have to find the an and bn first and then map it into Cn or theta n, or maybe find the alpha n first and then map it to Cn and theta n. So each form for Fourier series has its advantages and disadvantages. And what I suggest is that you understand all of them so that you can use the one that makes life easier for you. I myself like this one more because it is closer to the Fourier transform compared to the other forms. But I will try to give you exercises to practice for all the forms. I want you to understand all of them. But before we go into the details of those equations, which you have to understand really well, let me give you an illustration of the concept first. And to understand the two examples I'm going to show you, let's just look at this equation first, the compact Fourier series form, which says that if you have x of t periodic, you can write it as a DC plus a cosine n equal 1, plus another cosine n equal 2, plus another cosine n equal 3, n equal 4, n equal 5, n equal 6, and so on. You start adding cosines, cosines, cosines. What are the differences between those cosines you're adding? There are three differences. First, the frequency keeps changing. The first cosine has frequency omega naught, the fundamental, and then the next one has 2 omega naught, 3 omega naught, the third one, the fourth one 4 omega naught, 5 omega naught, 6 omega naught, and so on. What else is changing? The Cn, the amplitude, and the phase theta n. Those two, the amplitude and the phase, are different for the different cosines, and they are dependent on the x of t that you are analyzing. My first example is this x of t. This signal is familiar to you. It's a repeated rect signal. But I did a few changes to the unit rect. What I did here is amplitude scaling, multiply it by 5. So I go from 0 to 5. And I also scaled time by 4. So the pulse width is 4. And I shifted minus 2. That's why this repeated rect. does not have even symmetry around the vertical axis. But still, it's a repeated rect signal. And the fundamental period is 8 seconds. It repeats itself every 8 seconds. So I say to you, all right, you have this x of t. Can you rewrite it in a different form? And the answer is yes. Use Fourier series to represent x of t as an infinite sum of sinusoids. You could use the complex exponential form. You could use the trigonometric form. You could use the compact form. I'll concentrate on the compact form just for now, which means I say x of t is equal a DC value, constant C naught over 2, plus summation from 1 to infinity, constant Cn, cosine n omega naught t minus theta n. Notice I have infinity cosines, infinity sinusoidal signals, cosines with different amplitudes and different phase shifts. Not only that, the frequency is multiple of the fundamental. What is the fundamental frequency? I said the fundamental period is 8 seconds. That's why the fundamental frequency is 2 pi over 8 radian per second. Given you know that, let's start adding some components. I'll bring in a certain constant, a constant value, that's the DC value, plus I'll just add one sinusoidal signal, which is cosine 2 by t over 8 minus pi over 2. The cosine minus pi over 2 phase shift, that's minus 90 degrees, is actually a sine. So I'm actually adding a sine signal plus a constant. What happens if you get a sine signal plus a constant? You get a shifted sine signal, a shifted sine signal. This is not exactly our x of t. Our x of t was repeated rect, not exactly sine shifted upward, but there are similarities. Notice that I picked the amplitude 10 over pi. With the shift of 2.5, I'm reaching a little bit over 5. And here, I'm reaching a little bit beneath 0. So I'm going around 0 to 5, which was the amplitude of my rect. So I'm getting close with one sine, but not exactly rect. However, please notice that the period, which is 8 seconds, is also similar to the period here, which is 8 seconds. That's why I picked the fundamental frequency to be the frequency of my first cosine. But I also picked the amplitude and the phase carefully for the signal to have some similar characteristics to the repeated rect. Not exactly repeated rect yet, but it's quite similar. Later on, I'll teach you how to find the proper amplitude and the proper phase to start constructing the repeated rect. Now let's go one step further. I need more cosines. It's not enough to take one cosine, n equal 1. I need n equal 2, n equal 3, n equal 4, n equal 5, n equal 6, and so on. I need to go to infinity. I need infinity cosines. So here I start adding more cosines. I'll add this cosine here and this cosine here. This cosine here has frequency 2 times the fundamental. And this cosine here has frequency 3 times the fundamental. 3 times the fundamental, which is 2 pi over 8, gives you 6 pi over 8. I choose a certain amplitude for this cosine and a phase shift, and I choose a certain amplitude and a phase shift for this. For reasons hopefully you'll understand later, I picked the amplitude here to be 0, and that's why the whole term was zeroed out. Why did I do that? You'll understand why later on when we discuss how even and odd functions affect Fourier series calculations. Anyways, I have now this cosine and this cosine. This is higher frequency. Notice this is the first cosine that I had. I'm going to add another cosine with frequency 3 times the fundamental frequency. I'm going to add the DC value plus this cosine plus this cosine. What do I get? Try it out. You could use MATLAB. You could use your graphing calculator. You'll see that you're going to get this shape, which is now changing into something more like repeated rect. And you're still close to 5, you're still close to 0, and the fundamental period is 8 seconds. Let's try adding more cosines. This time, I'm going to add 2 more cosines. This one here is 4 times the fundamental frequency. This is 5 times the fundamental frequency. If you multiply 2 pi over 8 by 5, you get 10 pi over 8. and I picked a certain amplitude. Notice that for this particular example, the amplitude is going smaller. So the amplitude of this is bigger, this is smaller, this is smaller. This is typical for practical signals like the repeated drift. But I also picked the same phase shift, which is minus pi over 2. Do I have to pick always minus pi over 2? No, it just happens to be for this example. In the next example, you'll see we might pick other values. It depends on the actual signal. Now you could try it. You could use your graphing software, add this DC plus this cosine plus this cosine plus this cosine. Of course, we're adding more cosines that are zeros, which do not affect the diagram. What you're getting is this shape. Let's add more cosines. Here is another cosine. Here is another cosine. 7 times the fundamental frequency. This is the cosine with even a smaller amplitude. I'm going to add. This is what I'm getting. 2 more cosines. This one here and this one here. Of course, this is 0, does not affect you, but this one is here. You're getting this shape. If we add 2 more, I'm getting this shape. If you keep adding more cosines, though with different amplitudes and maybe sometimes different phase shifts, what you're getting is a shape closer and closer and closer to the original repeated drift. Notice we started with this simple sinusoidal signal, which was a sine, and now we are ending up with this shape. If we add more terms, we get even closer to the shape of a repeated drift. This one here shows you after I added 40 harmonics, 20 of course were zeros because I multiplied by amplitude of 0, plus 20 other cosines that are shifted actually sines, and this is what I get. Notice the ripple is going smaller and smaller and smaller, and I'm getting closer and closer and closer to the 5 here, 0 here. The fundamental period is 8 seconds. This is exactly the same shape that I started with. If you want to get a perfect repeated drift, you can do that, but you have to add infinity terms. Remember, the sum goes from n equal 1 to infinity. After you've added the infinity terms, you'll end up with your periodic signal repeated drift. This is the magic of Fourier series. Let me show you a second example, and I show you that Fourier series not only works for repeated drift, but works for other periodic signals. This time, I'm going to start with this signal, which is a repeated sawtooth. Repeat every 2 pi sawtooth t over 2 pi. Notice that the period is 2 pi, and I want my signal to go between pi and minus pi. Again, for simplicity, I'm going to stick with the compact form for Fourier series. I could use the trigonometric form or the complex exponential form equally well. They work perfectly fine, but this is easier for us to understand right now. I'm going to start with the DC value or average value of 0. I'm going to start with the first term, n equal 1. I'm going to add 2 cosine t minus pi over 2. Which is this cosine. Of course, minus pi over 2 makes it sine. Why am I picking sine here, not a cosine? The reason is that this is odd function. So I want to start with the odd sinusoidal signal, which is sine. Later on, you'll see that if I start with even function, I'll probably pick cosine instead of the sine. But I picked this cosine minus pi over 2, which is the sine, and I multiplied it by this 2. So 0 DC value plus the sine, I'm getting a sine. Because I picked 2, I'm still far away from pi and minus pi. But that's fine for now. You'll see later on things will change as I start adding more terms. However, please notice that the fundamental period is 2 pi, which is exactly the same as the fundamental period for my original signal, the repeated sawtooth signal. By the way, if your fundamental period is 2 pi, this means your fundamental frequency is 2 pi over 2 pi, which is 1. That's why my frequency is 1 for the first harmonic, the first cosine that I picked. Now let us add another cosine, because this does not look like a repeated sawtooth. Here I'm adding a cosine with a frequency equal 2 times the fundamental frequency. Notice this cosine I'm adding has 2 cycles for every cycle in this cosine, because the frequency here is double the frequency of the fundamental. And I also picked a different amplitude equal 1. Not only that, notice here I also picked a different phase shift. Instead of minus pi over 2, this time I picked plus pi over 2, which gives me minus sign. Please notice that the choice of amplitudes and phase shifts is dependent on the signal. You want to be able to add the cosines to give you the original periodic signal. And a very important skill you want to learn is how to calculate those amplitudes and those phase shifts for each signal. Now again, let's add another cosine. This time a 3 the fundamental, different amplitude, different phase shift. See what I'm getting? Closer to sawtooth. Not exactly sawtooth just yet, but we're getting closer. And notice we're getting closer to pi and minus pi after only adding 1 harmonic, 2 harmonics, 3 harmonics. If we add more, this is the 4th harmonic, different amplitude and different phase shift, we're getting closer. This is the 5th harmonic we're adding. And then another harmonic, 6 times t. 6 is the fundamental frequency, 1 radian per second multiplied by a factor of 6. Now I'm adding the 7th harmonic, followed by the 8th harmonic and the 9th harmonic. Notice I'm reducing the amplitude. Every time I'm increasing the frequency, I'm reducing the amplitude of the harmonic. Do I have to do that all the time? Not necessarily, but typically a lot of times as we go with the higher frequency for the harmonic, the amplitude gets smaller. Not always, but a lot of times. This is after adding the 10th harmonic here. Notice the shape, it's getting closer and closer to a repeated sawtooth. If you add 40 harmonics, 40 sinusoidal signals, after selecting the amplitude and the phase properly, what you're getting is very close to the desired repeated sawtooth signal with a little bit of ripple because I'm only adding 40 terms. As I add 60 terms, 80 terms, 1000 terms, 2000 terms, the ripple gets smaller and smaller and smaller until it becomes zero ripple as I go to infinity cosines. And that is Fourier series. Fourier series says that x of t periodic can be represented as infinite sum of cosines. Infinite sum of cosines. What I've shown you is the compact Fourier series form where I added the cosines from 1 to infinity and I changed the amplitude. I'm going to call it Cn, constant Cn, and I changed the phase shift minus theta n. By the way, please be careful as you solve exercises later on using the compact form because some textbooks use a different symbol for this amplitude and a different symbol for this phase shift. Not only that, some textbooks, instead of using minus theta n, they will use a plus a certain phase shift, let's say phi n. So please be careful which convention the textbook is using. If they are using plus phi n, the values they're getting for phi n will be different than mine with a negative sign because I'm using minus theta n. By the way, the other forms, the trigonometric form and the complex exponential form, mean the same thing. They are saying you can represent periodic signal x of t, not aperiodic, periodic signal x of t as infinite sum of cosines. And also notice that the fundamental frequency omega naught 2 pi over t naught is the same for all the equations. Alright, now you've seen the equations. Let's stop here for now. And in the next video, I'll show you that those 3 equations, even though they look different, they are actually quite similar and they are related to each other. What is this relationship? That's in the next video. Please leave any questions in the comment section. Goodbye for now.